start reading from now on, and I'm going to show you the things. I'm going to show you the things you need to read. Let me see. So we are using the textbook here, no matter which version you have, and then we are going to have read some things that is related to what we have learned. And we have learned something. It should be we have already learned the power method, the basic version, and what you are going to read. So for this chapter, you are going to read how to accelerate the convergence for the power methods, and also the symmetric power methods. And this is the part for the power methods, and inverse power methods as well. And that's it. And this is the 3 parts. Let me just write down. So this is a power method part, and then this is something you need to read the extra, and accelerating the convergence. And the second part is about the symmetric power method. And the inverse power method. They are all some power method based on the first very basic version. So I think you have the ability to understand the material here. Inverse power method. And this is the things. And I think that's all the things about the power method part. And the next part, it should be, let's skip the diffraction one. There are a lot of different methods here. Let's skip this part. And we have the householder method, we have the QR method, but we have already covered everything on this session. Let's see. And the QR method side just a little bit here. Let's see if we need to read something about the accelerating point. It's quite tricky, this part. Just skip it. This part is quite tricky. Where's the, let me see, where's the content part? The content part, okay. So also I need you to read something about this sessions. This is a sessions level 5. But you would expect that I would just have 2 to 3 questions on from this extra reading. So I believe that you don't need to read it, read the details by so far, and then you just go over all the session and then take a look at the idea for each methods and how to accelerate the convergence. If you have some things you cannot understand the details, and then let's just skip it first. And then once you get the final exam questions, and then you can work on the details. So you don't need to understand all the things in this chapters, in these sessions, but you need to know what is the general idea there before you get the final exam questions. And then once you get the final exam question, and then you can work on the details. Because it takes a lot of time to read all the details here, but you don't need all the details for the questions. But I will release the questions next week. Next week? 6. It's 7 June. The day should be 7 June. The day I release the final exam. And you need to submit your final exams on 15 June. And so let's see, this is a singular value decomposition. And this is also one thing you need to read. And we also talk about the things here is how to solve the root problem, find a root here, and then the bisection method is 2.0, and then we are not going to read some things about it. And then let's see, is there any extra things we can read for the fixed point problem? I don't think so. Yeah, and for the Newton's method, and then it could be some variation here. There's a convergence result, and then we have already mentioned the sequence method, and then we'll go back to the format of the formula later. And okay, so this is something you might need to read. The force precision methods is also based on the Newton's method. Let me see. Is this a say somebody? Yes. So this is the session 2.3, and it's under the Newton's method session, and then you need to read the force positions. Just get the general idea for this one. And later on, I will mention on your text, and then I will mention, okay, it's about the force positions method, and then blah blah blah, and then this question, and how to calculate something, and then looks like this. So what you need to do in this week is to just get the general idea for each session, and once you get the question, and then you can quickly know which part you need to read, and then you know what you are expecting in that sections, and that's it. And so there are a lot of sessions here, but you don't need to read the details. You just need to know the idea before the questions you get. So the next part should be, this is quite lengthy. I don't want you to read this part. And there's some things we are doing this week. And we skip anything in the class teaching. Error bounds. Okay, error bounds, and then it's quite lengthy part. I don't think there is some things you might need to read for this part. So I guess, and then that's all the things you might need to read for the final exam. And also I will include like 2 questions about what we have already learned in the class. And 2 questions, it means that big questions, and then you have some small parts here. Maybe one question, one big question, and then you have 5 small parts, and that could happen. And also, because this quarter we include the coding part, and you will also expect one coding questions, and you never see the coding question before. And so I will also include one coding questions in your final exam. So maybe the questions could be released on 6 June or 7 June. And then you might have 8 to 9 days to finish it. That's all the things. It's take home, and it could be very difficult and challenging. And this is something different from the in class one. So next, I'm going to go back to our lecture. First, I need to open one website for you. Okay, so it happens that last time I mentioned that maybe let's try to bump the second adaptive, but later on I'll find out that this is not the general things we can do, and it only works for some special cases if you want to get the second adaptive bumped from the original problem, not knowing the exact solutions. So let's see. Let's go back to the examples we have last time, and then we want to find out the BAMs for the error BAMs for the. Oops, where's my pen? Let me think about where's my pen. Oh. Let's see, this is the notes. And it shows well the problem. Okay, good. So let's see, stop sharing. This is the things we talked about last time. And then we have the example 2. And this is the 31.5.9, and then we want to get the error BAMs for these questions. And last time I just tried very hard to figure out the L constant. This is the Lipschitz constant, and this is the MM is the second derivative of the second problem. And I expect that I can do some things to calculate the second derivative, and then the second derivative here. But it happens that without knowing the exact solutions for these questions, I cannot get the BAM for the second derivative. And also, one thing you can use. So for this kind of questions, maybe you can have. So here there's some things, but all the things is based on the exact solutions format. And you will see here, if you, I will post this link later. And then all the things is based on the format of the solution, and then you can use some ODE knowledge to solve this type of the question. This is the partial linear differential equations, and here it uses the solutions format, and then to estimate the second derivative, to give the solution BAM. And so it could BAM the y function, and then if we can BAM the y function, and then we can also BAM the second derivative, and that's my idea. But here at the end of the day, the AM and K is just the BAM for the, let me see, So the capital M should be the so the capital M is the bound for the Bx. And here the small k should be the smaller bound. The lower bound for the AX, and then this is the upper bound for the BX. And at the end of the day, and then you will find out the y function is bounded by the M over K. And let me just copy all the things down. And then on with this link, and then it shows you how to prove it. But actually, for the specific questions, you just need to calculate the exact solution. And I'm not sure if your calculator is able to do it, but because the final exam is take home, so if you don't know how to calculate the exact solution, and that's one solution for you, and then you can go to the, let me see, you can go to here. So I'm not going to give you some things. If I'm asking you to give the error RAM, and then and you need to use the if you need to use the exact solution, and then one remedy here is to use this one. Solve the ODE problem. Initial value problem, and then you can go to this website, Wolfram Alpha, and then you can use such tools here, specify initial value. So for examples, you can go to this website and then enter what you have. So for examples, what we have here, and then you can have the you can enter your equation here, and then enter your initial value here, and then it will solve the equation for you, and then you will get the solution. And this is one remedy for you. And then another remedy is to use your ODE class knowledge to solve the equation. And this is another one remedy. And so I don't think it's general. It is not general to get the secondary from the questions itself. So what you can do here, let's go back to here. But sometimes we don't need the exact solution to get the second derivative bomb. And this is one situation. I give you one example here. And so for example, you have the what's the example number here? Example 2. So example 3. Let's say the y prime t and then equals to t minus sine t, sine yt. And let's the y0 equals to 0. And in this way, and then for this example, we want to get the second derivative prime, and then let's see what happens here. The second derivative prime, and we should keep in mind that the y is a function of t. So let's get the derivative, and then that is the derivative regarding to the y t variables. So for the first item, we get 1. And then second item, we have sine. We are going to use the chain rule. Here it should be cosine y. So this is the d sine y, and then dy, and the dy dt. And which means that we have cosine yt and y prime t. And from the equation here, we already know that the y prime t equals to, also I need to specify the interval we are working in. The time is in between 0 and 2. And for this example, we have cosine yt, and then the y prime t from the equation, the question statement, and then we have is equals to t minus sine yt. And we are bounding this y prime t absolute value. So at the end of the day, and then it's bounded by 1 plus the cosine yt, and the absolute value, and the t absolute value plus cosine yt is smaller than or equals to, and then sine YT, and the absolute value. And as you can see here, we have the cosine function, sine function, and then they are bounded by one, and then times a t. And but the t absolute value here, the biggest possible value is 2. So we have 2 here. And then the last item, cosine, and this times sine, and then their biggest value should be also 1 times 1. And so at the end of the day, you will see for this specific questions, you don't even need to know the exact solutions, and then you get the bound for the second derivative. But this is a very special case. And the other cases, I believe that if we want to use the theorem 5.9 to bound the error, and then actually for this one, we need to know the exact solution. And I'm not sure. I believe there's some more specific initial value problem, and then we don't need to know the we don't even need to know the exact solution, and then we can bound it. And of course we can do it, but it's some specific and special cases there. But here, if we want to use the theorem 5.9, and then usually you need to get the exact solution and then bound the error. And here for this one, the textbooks is already given the exact solution. And then the exact solutions for this question is this. And after we calculate the second derivative and then bound it, and then you will see the bound should be the things we write out here. Exponential to and this is the things, one things. I just want to explain some things I mentioned last time. This time I also figure out that one student or several students come to my office hour, and I figure out that there's some things they make the mistakes. So let's see here. I mentioned that if we want to get the derivative of the t, the f function, and then the derivative of f functions regarding the t, and the f function is a function of t, and then it's also functions of yt. And this is a multi-variables function. You have the t variable and the y variable, but the t variable is depending on t, and then the y variable is also depending on the variable y. And if you go to take a look at the chain rule in multi-variable and multi-variables calculus, and then you will figure out that if we want to calculate this function derivative, and then it should be the derivative of that, and then regarding the t variable only, and then plus the derivative of that regarding to the y variable, and then times the y variables, and then derivative of y variable, and then regarding to the t variables. And but the derivative of the y regarding to the t variable is equals to the ft yt. So we have this here. And why do I mention this? Because on your homework, some people make such a mistakes. Don't mind I list your mistake here. It could be very common, so don't even mind I present your maybe some office hours mistake here, because I think this is very common. And let's go to take a look at here. It should be the what questions we have on the. It should be the initial value problem. Euler's mapper. Okay, this is the questions we have. It should be the back question. should be here. Okay, it's this one. So for example, so on your homework, I forgot which questions I'm giving to you, and but I'm going to just copy down one thing here. I believe this questions. So on your homework, and then there's some common mistake here. Example 2. Example 4. And then this is the homework question, and then you might get some common mistake here. This is your homework question, y prime t, and then 2 over t, y, and then plus the t squared, and then et. And when you want to write out the Euler's methods, and then the Euler's methods, it has such a formula here. Let me just copy down the Euler's methods formula. It should be the wi plus 1. This is not the problem here. I think the problem you might have, it should be there another derivative. So this is the A, and then the Euler's methods. And then the Euler's methods, it does not require you to calculate the derivative. Wi, and then plus hi, fgi, and then wi. But I also mentioned some Taylor's higher order method there with higher order. And for those questions, and then you might need to calculate more items here. And then that more items, it requires you to calculate the derivative of the f. So let me copy down the idea here. And then the updating rule should be wi plus 1, and then equals to wi and then h. I think this one should be something similar to the Taylor expansion here. Let's say we just have the order n here, and order 2 here. And we have the h over 2, and then the first derivative of the t wi. And you will figure out that we need to calculate the first derivative. And this notation is quite confusing. The textbook notation is quite confusing. And so I am going to use the dfdt here to specify this is derivative regarding to the t variable. And so now if we want to get the derivative, this is the f part, the f function part. And if I want to get the derivative of the t, and then this is a function of ty. So if I want to get the derivative of the function, and then regarding to the t variable, and then this is how I do it. So what you need to pay attention to is that this is a function of t, the y is a function of t. So for the first part, if we want to get the derivative of the function ty, fty, and then the first part should be, okay, we have the product here, and then this is 2, it's the product of 2 function, and then it's all about the t function. It's all about a function of t. And we have the product here, so we are going to apply the product rule. And the first part, the derivative, it should be -1, and then 2, and then t -2, right? Yes. So this is the derivative of the first part. The first part in the first item of the first part. And we take the derivative of the y, that is the dy dt here. And then times the t over 2 over t. And this is the original version of the first part in the first item. And so this is the things. And the rest of things are the same. And then you apply the product rule here, but I think you are good at doing the derivative here. This part, doing the derivative of the t squared et here, and then use the product rule to calculate the this derivative, and then I will leave this part to you. But I'm just pointing out that what you need to do for this derivative of this part is that you need to get the derivative of the first part in this first item, and then times the original one, the original y, and then get the derivative of the y, and then times the original part in the first part of the item. And this is the things you need to be very careful here. And then for the dy dt, this is the derivative of y. And from the original equation, and then you can change this part too. So this is the things, and you need to use the equation again, and then the derivative of the y equals to 2 over t, and then yt, and then plus the t squared et, and 2 over t here, and then I just copy down the things we have, and you can see I just changed the derivative of y, and then to this expressions by using the original equation here, the original problem here. And this is the things, be very careful. And I saw some common mistake here. So the common mistake is that the people, they could get this wrong. They just calculate the derivative of the first part, and then they treat the y function as a constant, and then it write it in this way. They write it in this way, and then they go to the second part, and then calculate the derivative. And they ignore the fact that this is also a function of t, and this is the wrong answer. And this is the correct answer. Use the product rule. Any question here? This is one common mistake I saw in the office hour. And the next things I want to mention today is, let's see, I have already mentioned the, this part, it should be the nth order Taylor's method, and for the example, let me see. Okay, I'm just going to show you one example for the Taylor's method, the Taylor's method higher order. And here, let's see. Let's apply the Taylor's method. But you will see this example is quite simple, and then it's not comparable to your questions on your homework. This is just one simple example here, and then apply the Taylor's methods of the order 2 to the initial value problem here, and then that is the y prime equals to y prime t, and then yt minus t squared plus 1, and then 0 tier 2, and then our initial value should be 0.5. And let's see. Let's go back to what we have here. This is the general format, and then we have the wi plus 1, and then wi, and then plus all the way to there. And so I'm going to copy down this formula, and we want the order to the 2, so we should have h2 here. So this is the formula, and we want the order to the 2, so which means that we are going to calculate all the things here, and then up to the 2 item, the h2 item. And am I right? Yes, actually, am I right here? So all the things up to the h2, and then divided by 2. And now I'm going to, I already know the FTI, the F function, and then what I need to know is the derivative of F, and then regarding to the variable t. So I'm going to calculate the derivative here, and also I set up the W0 here as the initial conditions. And this is the setting here for the second order of the Taylor's methods. I copy down the formula, and then I write down the initial condition. And now I'm going to calculate the derivative of the f. And what's my f function? F function is just the fty equals to the right hand side yt and then minus t squared plus 1. And if I calculate the derivative here, and then it's just the derivative of the y regarding to the t variable, and then minus the 2t. And the dy dt, and then from the initial value problem, and then we got that the derivative of the y, and then it equals to the yt, and then minus t squared plus 1, and then minus 2t. This is the things, and this is the first derivative. So what we have right now, let's do some plugging here. And then so what we have is wi plus 1, and then equals to the wi, and then what is the fti wi? And then we just replace the t with tei here, and then we replace the y with wi in this function. And so we got fti y wi, and then we have wi for the y variable, and then minus the ti squared, and then plus 1. And the next I got, let's see, actually I have two, this is h. And then h squared divided by 2. I'm going to write down this, write this formula here. And then with the functions, I already know the dfdt here. And so the next part, it should be the derivative of the f function, and then evaluate at, so this one is a function of t and y. And but we are going to replace the t with ti, and then replace the y with the wi. So what I have here, it should be so the expression here, and then I got wi, and then minus the ti squared, and then plus 1, and then minus 2i ti. And so this is the formula we are going to use to calculate the apply the Taylor's methods. And don't forget that there's one more assumption here. With the nodal points, with 10 nodal points, n equals to 10, which means that we have 11 nodal points here, and 11 nodal points is x0, t0, t1, t2, and then to the t11, and then to the t10. So here, what's the step size? The step size is just the h, and then 2 minus 0, this is the interval length, and then divided by the 10 subinterval. So for each subinterval, the h size, it should be 0.2. And so now we can start our iteration, and then with such a formula, and I will just let the, this is how we get this formula, and then I will just let the iterations, details, calculations, and for you, or you can take a look at the textbooks result, and then I will just give you the formula here, and then exercise, and then we already get the exercise over there. And this is the formula, updating formula, and now with the W0 equals to 0.5. And this is all the things for this example. And for the concrete calculation, I would just leave you to read the textbooks. And the next part, let me see. The next part, it should be compare the things we have. So the next part, it should be to compare the things we have for the very first. So there's one concept is about the truncation errors. And let's see what is the Euler's method's truncation error, and also what is the truncation error for the Taylor's higher order item. So first of all, we need the definition of the truncation error, and why do you do this in the notes now? That's the problem. Okay, never mind. So what we are going to do is to take a look at here. The original equation is the y prime t and then equals to the ft, and then y a equals to the alpha. And let's go to what we have here, the truncation error. And this is the t, and then it's between the a and then between the b. And we have the initial value. And the definitions of the truncation error is local truncation error. And as you can see in the formula in the Euler's method and the Taylor's methods, and actually we have the approximation scheme looks like this. W0, and then it equals to the initial value. And we have the updating rule, and then the Wi plus 1, and then equals to the Wi, and then plus the h size, and then phi is the updating rule, and then but in the Taylor's method we have the Tn there, and phi, and then Ti, and then Wi. And this is the updating rule. And let's see, let's compare what we have, and also compare to the actual equations. And so we define the local truncation error in this format, and then the local truncation error is just the, so we use the tau I plus 1h to represent the local truncation error, and then that is the yi plus 1 minus, which means that we substitute this is yi plus 1, and which means that the y divided at the time ti plus 1. And let's plot in the exact solution and to such an formula, and then to see how far do we get to the exact equation, exact solution. So let's plug in the yi plus 1 to that equation, and then let's plug in the yi to this equation, and then there we get the area here. So on the right hand side, we should have the yi, and then plus the h, and then phi ti, and then yi. And this is the things. And also we also want to divide this by h. So at the end of the day, and then you will find out that the truncation error we can write in this way: yi plus 1, and then minus the yi divided by h, and then plus the phi ti yi. And this is a local truncation error. And let's see, so this is a definition, and we are going to take a look at the local truncation error for the Taylor's methods. So for the Taylor's methods of order n, and the local truncation error we have, it should be, at the end of the day, if you calculate such a formula here, the right-hand side formula here, and then you will find out that the error is it's an n order error. h to the order of n error. And then we have the big O here. And if you want to prove this, and then it's quite easy. And let's go back to the formula we have here. So actually you have the Taylor expansion. And then we go from the Taylor expansions to the Taylor's methods. So let's copy them the Taylor expansion here. And then that's the things. And if we want to, so this is the n+1 Taylor expansion here. And if, so let's move the things around, and then actually you will see that this part is just the Taylor Tn and then Tn expressions in the or the 5T yi expressions in the Taylor's methods. So let's move the things around, and then you will see this. So I'm going to move the things around and move all the things to the left-hand side. And so which means that this is going to the right-hand side, the equal size is here. And then all the other things is minus the whole things here. And then there's an equal size here. And then I'm going to divide both sides by h, and then I arrive to these expressions, the local truncations error expressions here. So at the end, you would get yti plus 1, and then minus yti, and then divided by h. And the rest of all is just the, so for this expression here, it's just a tn and then tiyi expressions. And then I have already defined the tn expressions before. And on the right hand side, if we divide both sides by h, and then you will see this one is hn, and this one is n+1 factorial, and this one is the n+1, and then cos ci. And we also have one assumption here about this theorem. This is a theorem 5.12, and there's one assumption here about the y function. We assume that the y is the continuous n+1 continuous functions on the interval AB. And because it's a continuous function, and then the n+1 derivative is a continuous function, and then we can expect that this item is bounded. Hence, at the end of the day, the error term, the tau I+1h is OHN item. And this is the idea to prove it. And if you want to see the details proofs, and then you can refer to the textbook. But the idea is that you just make use of the Taylor expansion and then move the things around. And then you'll figure out that this part, all the things on the left-hand side divided by h, and then this is the Tn part. And then the yti+1 minus yti divided by h is here. And this is the definitions of the tau I+1. And so this is the left-hand side part, and then the right-hand side part is to the order of n. And this is because this part is bounded, this one is bounded, it's not infinity, because this part, the y functions, the n+1 derivative of the y is a continuous function. And this is all the things about the Taylor's expansion, Taylor's methods. We cover the n order methods, and then we cover the error term here. And all the things you just need to know is that the Taylor's methods, the local truncation error is order to the order of n. And also, we also need to be very, very careful about the derivative of the f, and then regarding to the t variable. And also, there's also one question about the homework. And then the student asked me how to calculate the Lipschitz constant. And actually, if this is the f function is a continuous function, and then you actually can get the derivative of the y. And then once you get the derivative, and then you can bound the derivative there. And then once you get the bound for the derivative, and then that is the constant L. And there's one theorem on the textbook is the theorem 5.3, and that is about why this derivative is the constant, why this is the BAM of this derivative is a Lipschitz continuous BAM, and it's you can use the mean value theorem to prove the theorem 5.3 there. And this is the things about the homework again. And this is all the things I want to mention today. And any questions? So this is the one last thing I want to mention, how to calculate. Maybe one method is to find out the Lipschitz constant, just to bound the first derivative. And this is something about the theorem 5.3 and on the test run. Let me see, it should be 5.3. And then the 5.3 is using the mean value theorem. Any questions? If you don't have any questions, you are safe to leave. And then if you have any questions, please come over here. Let me take the picture. Question. Textbook 吗？大概会有2道，
大概
不会太多，就会2道，然后2道或者3道吧，2道或者3道，但是我不能确定，因为我还没调整那个翻录上的难度。
那我们主要就是proof还是
啊？
就是 textbook 题或者proof还是
都会有。proof 肯定会有 ，proof 肯定会有，因为我要把那个难度调上去，因为是 take on。
那这个是什么？这不是上次讲？
上次没有讲这个东西，这个是讲我们要怎么找到那个 Lipschitz constant。然后 theorem 5.3 we haven't mentioned it in the class, but this is useful in your homework. 就是 you can bound the first derivative of the y, and then you will find out the Lipschitz constant. 因为 Lipschitz constant 的定义也不一样嘛。Lipschitz constant 是2个相减，然后小等于 L， 然后那个 variable 的相减嘛，对吧？然后但是其实我们是可以用这个东西去找到那个 Lipschitz constant， 就是只要帮助 first derivative。
一个问题是上的
是谁？这是什么东西？
这是上个作业。
这是那个 solution 还是你写的？
这是
首先你如果觉得那个作业批的不好，你 send 那个 email 给我，他可能会按照他自己理解来改，所以你懂吗？
行。
然后第二，为什么他会帮呢 ？P0 他们就是一个因为就是那个如果没错就是 Newton's method right 还是 fixed point？
所以是
fixed point 嘛，最后就是对吗？那个
对第二题
是一个 fixed point，
第3
right？
项对
fixed point 它是将你的东西都是 map 到它的 interval 里面的嘛，对不对？所以你 P0 P1 都在那个0到2派的那个区间里面。
我是代入了，就是 P 等于 GP0，然后比如说1。
对啊，可以啊，所以是对的呀。
但是他的答案就是他把这个
他把它更
乘2派了，就只剩2派了。
对，它是更大了嘛。
对，
我知道，所以我就说你可以
提
交个 request 给我。
这答案就会更小。
答案会更宽，因为它对于的是任意情况下的，你对于的是那个 estimate 是你的你取定的 P0 的那个情况的，懂吗？它如果2派的话，你取定任意的 P0 都可以帮助嘛。应该是 你现在只是 analyze 你 B 问题里面的那个 estimate 那个 iteration number 吗？你 B question 里面你用的 coding，你的 P0 是什么这样子？所以你对的，
行，
只是它会更宽泛而已，它答案
这
more general cases。
Question that can show us the exact solution of this problem. Can I see that?
OK，
I used the website they were just showing me, and I got this, but they have the constancy.
do you plug in their initial value there?
Oh, this I
Yeah.
didn't. Okay, I will do that.
So that's why you have the constant.
And then for this one, are we like the example that we just did? Are we trying to find the n?
Yes, we are trying to avoid the n, but sometimes we can do it in this way. This is very special cases, but if you cannot find the second derivative with this methods, just calculate the second derivative from the original questions. If you cannot do this, and then you can resolve,
Exact solution.
you can go to the website and then calculate the.
So let's say I want to opposite hour. So the m we should use the exact solution, and the I'll use the original given.
Yeah.
Okay.
But if you are able to calculate second derivative bound, and then from just the original problem, and then you can definitely do that.
The answer will be the same.
Would be the
M?
same.
Okay.
Maybe I have to say, maybe you will get a more bigger M here.
So try this first. If you cannot get it, then use the exact
Yeah,
solution.
yeah.
Okay. And then
Stop. Sorry, first.
the air bond